Hi, and this is the final video in this topic. And on the right hand side you see here a picture of a MRI scanner, MRI standing for magnetic resonance image. And that's technology there has been developed out of NMR, nuclear magnetic resonance. And this particular bit of NMR that we're going to do is carbon-13. Now, carbon-13 is an isotope of carbon. It's not the common isotope. The common isotope is carbon-12, of course. Carbon-13 makes up about 1% of the carbon on the planet. And yet, in a sample of molecules, there will be enough carbon-13 nuclei to make this work. So what we're going to do is we're going to have a look at the number of peaks. And straight off, what we can say is that carbon-13 NMR is much easier than proton NMR. Because we've got no splitting and we've got no integrals to worry about. It's just the number of peaks. And that does enable us to differentiate between isomers, which we'll have a look at as well. So determining the number of peaks is the main job that we have when we're looking at carbon-13 spectra. And we're going to have our table to refer to. That's the table of chemical shifts. Notice these chemical shifts are different sort of numbers, different scale, so they're sort of in the range of 5 or 10, right up to 200 or 300. And but it works in the same way. So we could draw out a spectrum for a molecule here. So in the same way, 0 is going to be our reference, which is also TMS, tetramethylsilane. And let's say we've got 25, 50, 75 and 100 sort of scale. And we might have a peak at about 20, so a peak at 20. We might have a peak at 51 and another peak at about 67. So let's draw the molecule for this spectrum, which is 1-chloropropan-2-ol. So 1-chloropropan-2-ol has 3 carbons. It's propan-2-ol, so our hydroxyl group is coming off the second carbon, and our 1-chloro comes off the first carbon, like so. The rest are hydrogens. And there we have our molecule of 1-chloropropan-2-ol. Let's write the name out as well, why not? 1-chloropropan-2-ol. And there it is. So now let's just look at the different environments of our carbon atoms, nuclei. So this carbon here is a methyl carbon, and here we have a methyl carbon, and so hey presto, the range between 5 and 40 fits this. So our chemical shift for this carbon is the peak there at about 20. Okay, let's move on to the next carbon. Let's look at this carbon here. This carbon is attached to an oxygen, and so if we have a look at this one here, we can say this carbon is attached to an oxygen in an alcohol. Also works with ethers and esters, the oxygens that are involved in an ether or an ester. But so that's our peak. That's at sigma equal to 67. So then let's have a look at our third carbon here. This carbon here, this purple carbon that we've ringed, is in one of these groups. So we've got a carbon attached to a chlorine between 10 and 70, and so that corresponds to our peak of 51. So our shift is 51 for that carbon there. So this, and you can see that, right, so there's the purple one, that 51, the green one is this peak there, and our red carbon matches that peak there. Let's do another couple of examples just in terms of number of peaks. If we have a look at propanone. Propanone we could draw out, it's 3 carbons. It's a ketone, so the group has to be in the middle of the chain, and then we've got hydrogens off here, right? And you can see that there are 2 different environments for the 3 carbons that are in propanone, right? So this carbon here is in the same chemical environment as that carbon there, so they're going to make 1 peak. Those 2 carbons are going to make 1 peak, whereas the carbon that's attached to the oxygen with a double bond, the carbonyl carbon, that's going to have its own peak. So that you would see 2 peaks for propanone. We've got space for one more example here. Let's do propanal. Determine the number of peaks for propanal. Let's draw it out. So again, we've got 3 carbons, but at this time the carbonyl group is on the end, and because it's an aldehyde, and the rest are hydrogens. So this is our propanal. All right. How many chemically equivalent environments have we got? So this is 1, right? And there are no other carbons within that same environment. And a CH2 is going to be in its own environment as well, because the methyl carbon there is not chemically equivalent to the CH2 group. So we've got 3 different environments for our 3 carbons there, so we're going to have 3 peaks. Well, we've got a tiny bit more space there. Let's do benzene as well. So benzene. All right. So we'll quickly draw out benzene. Hexagonal, 6 carbons in a hexagon, and with the delocalized electrons. You can see that this is a very symmetric molecule, and so all carbon atoms, all 6 carbon atoms, are actually in the same environment, and so benzene will just make 1 peak, as would cyclohexane. Cyclohexane is symmetrical in the same way as benzene is, so that would be 1 peak. But substituted benzene products would be different, so let's have a look at a few of those. Let's do methyl benzene this time. So we've substituted on a methyl group, and let's draw that out. We've got our methyl group, and that's attached to a benzene ring, like so. So in red, I'm going to draw the number of chemically equivalent environments. And so these numbers are not like the normal carbon numbering when we're naming a molecule. So we've got this carbon here would be in environment number 1, and that would be different to this carbon here, which we can say is in environment number 2. These 2 carbons that I'm just circling now, they are equivalent because of the symmetry of the molecule, but they would be different to the other environments, so we can give them both number 3. These 2 carbons are also equivalent to each other, but different from all the others, so they're in environment 4, and this last one here is on its own again, so that's a different environment again. So we would see 5 peaks. We would see 5 peaks for toluene here. Toluene is the other name for methyl benzene, of course. Let's do another example. Let's do 1,4-dimethyl benzene. So 1,4-dimethyl benzene. And seeing as I'm naming this one, let's name this one. Save me writing it out. Let's write it as toluene, methyl benzene. This is 1,4-dimethyl benzene. So let's draw our benzene ring. We'll make this our carbon number 1. So we've got one of our methyl groups there. So in green, I'll number my carbons. So that's 1, at least around the ring. 2, 3, 4, 5, 6. So the green numbers are the numbers of the carbons for naming purposes. And so if it's 1,4-dimethyl benzene, the other methyl group is going to come off carbon 4, which is like so. So that said, now let's work out how many peaks we'd expect to see on a spectrum. So the carbons in the methyl groups, like this one and this one, they are identical. So that is going to be environment number 1. And then the carbons that the methyl groups are attached to, they're also identical because of the symmetry of this molecule. So they're going to be environment number 2. If we take these carbons, aren't they the same as those carbons? So all of those 4 carbons are in environment 3. Like so. So I think we've got 3 peaks for 1,4-dimethyl benzene. Let's do another one though. Let's do an isomer, position isomer of 1,4-dimethyl benzene. Let's do 1,2-dimethyl benzene. So let's do 1,2-dimethyl benzene, like so. Let's just put our little dashes in there. So first thing is to draw it out. We start with drawing our benzene ring. There's a benzene ring, and this time, okay, so in green, as before, let's number our carbons. 1, 2, 3, 4, 5, 6. That's just the molecule naming numbering. So we're now going to do our 2 methyl groups. As the name suggests, we've got one methyl group coming off carbon number 1, and we've got another methyl group coming off carbon number 2. So that's our 1,2-dimethyl benzene. Now in red we will count the number of environments and therefore the number of peaks. You can possibly see a line of symmetry going through in that direction. Right, so you can see this carbon and this carbon are both going to be in identical environments. Let's call that environment number 1, so that will be 1 peak. And these 2 carbons here are also identical, so they're going to be environment number 2. These 2 carbons here are going to be environment number 3, and these 2 carbons here are going to be environment number 4. So 4 peaks for 1,2-dimethyl benzene, whereas its isomer 1,4-dimethyl benzene would have only 3 peaks. So that just about completes what we need to say about carbon-13 NMR. Last thing, let's just mention solvents, so the solvent for the molecule. And in both proton and carbon-13 NMR, often the solvent, so recognize that we're not talking about TMS, which is the standard. We're now talking about the solvent. Solvent is often this compound here, CdCl3, right, where D is an isotope of hydrogen called deuterium. DEU, deuterium, spelled like that. And so this compound would be deuterated trichloromethane. Deuterated trichloromethane. And it would look like this. So the D for the hydrogen isotope there, and 3 chlorines, like so. So that would be a solvent, and that's a particularly good solvent for proton NMR, because deuterium having an even mass number, so deuterium has an even mass number, an even mass number, which is 2, of course, in deuterium's case, 1 proton, 1 neutron. That doesn't make a peak in a proton spectrum. It will make this compound, deuterated trichloromethane, will make a peak in and so it will make a peak in a carbon-13 spectrum. But it's easily isolated and removed. So in the spectrums that you'll be given, you won't have the confusion of having to take out that peak for the carbon nucleus that is in deuterated trichloromethane. Okay, so that's it, I think, for carbon-13 NMR.